Yeah, good evening. From the last lecture, we'll continue the same chapter, chemical bonding. Till now in chemical bonding, we have just seen the meaning of ionic bond. We have seen the definition of lattice energy. We have compared lattice energy, percentage ionic character and covalent character. And in valence bond theory, we have just started how we have formation of covalent bond, which is the overlapping of orbital. In the case of overlapping of half-filled orbital, we have formation of covalent bond, and depending on the orientation of overlapping, it may be sigma bond and it may be pi bond. Sigma bond consists axial overlapping of half-filled orbital, and pi bond consists sideways overlapping of half-filled orbitals. In today's lecture, we'll continue with concept of sigma and pi bond and the lone pair of electron, and then we'll use the same concept in VS-EPR theory. This is the theory which decide the geometry about central atom, and we'll start hybrid state also, hybridization state. So hybridized state is the theory, a hypothetical concept to explain the geometry according to VS-EPR theory. So first we'll do the revision of whatever we have done in the last lecture related to number of sigma bonds, pi bonds, something like this. So as per sigma and if you remember, if we have suppose carbon-carbon single bond, suppose if we have carbon-carbon double bond, if we have, let's say, carbon-carbon triple bond. So first bond is always the sigma bond. So here you can say it is nothing but one sigma bond. It is nothing but one sigma and one pi bond. And it is nothing but one sigma bond. And let's say we have two pi bond. So we have one sigma bond, we have one sigma, one pi bond, we have one sigma and let's say two pi bond. Similarly, if we have to count the number of sigma bond, pi bond and lone pair of electron in, let's say example maybe suppose sulfate ion. Sulfate ion consists, let's say this as a geometry. Yeah, this as the bonding. In the case of sulfur is forming total 6 bond with oxygen. 2 oxygen forming complete 2 bonds, and that's why 2 oxygen consists additional negative charge. In this case, your number of sigma bonds. Here number of sigma bonds is, let's say 4 is the number of sigma bonds here. Same as number of pi bond. The number of pi bonds is 2 here. And similarly, if you see number of lone pair of electron should be. Now, as per oxygen is concerned, as oxygen consists 6 electron in their valence shell. Out of 6 electron, 1 forming sigma, 1 forming pi. So 4 electrons remaining means 2 lone pair of electron, and another 2 lone pair of electron here, 3 lone pair of electron, and another 3 lone pair of electron here. So as per total lone pair of electron is concerned, it is 3, 3, 6, 6 plus 2, 8 plus 2, 10. Total lone pair of electron is found to be 10 lone pair of electron. So in the case of sulfate ion, you can find out number of sigma bond, you can find out number of pi bond, you can find out number of lone pair of electron here. Similar type of calculation you can do for, ozone O3. Ozone having one of the structure as this oxygen carry positive charge, this oxygen carry negative charge. So as per number of sigma bond is concerned, it is forming 2 sigma bond in total. It consists 1 pi bond. Since out of double bond, 1 bond is going to be sigma and another bond is going to be pi. Now if you see the lone pair of electron, Again, this oxygen should have 2 lone pair of electron, since out of 6 electron in its valence shell, 2 electron participate in bonding, so 4 electron remaining, 2 lone pair of electron. As per this oxygen atom it consists of 1 lone pair of electron, and same as this oxygen atom is concerned, it consists 3 lone pair of electron. So it has 2 sigma bond, 1 pi bond, and as per total lone pair of electron is concerned, it has 6 lone pair of electron. So 1 sigma, 1 sigma, 1 pi, it has 1 sigma, 2 pi in sulfate ion. Number of sigma bond is 4, number of pi bond is 2, and number of lone pair of electron is found to be 10. Okay, I hope you understand the concept of how we count number of sigma bond, pi bond, and lone pair of electron. The next thing related to chemical bonding is, VSEPR theory. It is valence shell electron pair repulsion theory. So it is VSEPR. It is valence shell electron pair repulsion theory. VSEPR theory. So, its first postulate is geometry or shape of, any molecule or ion. Any molecule or ion, around central atom. Around central atom is decided by geometry or shape of any molecule or ion around central atom is decided by mutual repulsion. Is decided by mutual repulsion between paired electron of decided by mutual repulsion between paired electron of valence shell. Valence shell of central atom. Paired electron means it may be lone pair of electron also, it may be bond pair of electron also. And obviously in most stable geometry, this bond pair, lone pair, or repulsion between paired electrons should be minimum. Repulsion between paired electrons is minimum. So in most stable geometry, repulsion between paired electron is minimum. Further, next point is, for same angle between paired electron, for same angle between paired electron, this repulsion follow given order. The magnitude of repulsion follow given order. So if you see lone pair repulsion is found to be more than that of lone pair bond pair repulsion is found to be more than that of bond pair repulsion. So overall, if you see lone pair repulsion is more than lone pair bond pair repulsion is more than that of bond pair repulsion. So for same angle between paired electron, this repulsion follow given order. Lone pair repulsion is more than lone pair bond pair repulsion is more than bond pair repulsion. I hope you understand the concept. In most stable geometry, repulsion between paired electron is minimum. Geometry or shape of any molecule around central atom is decided by mutual repulsion between paired electron of valence shell. And for same angle between paired electron, this repulsion follow lone pair is more than lone pair bond pair, more than that of bond pair repulsion. One more postulate related to this is, as angle between paired electron increases, as angle between paired electron increases their repulsion. Their repulsion decreases sharply. So as angle between paired electron increases, their repulsion decreases sharply. So you can say repulsion at 90-degree angle will be much more significant than repulsion at 120-degree angle, and repulsion at 120-degree angle can be much more dominating in comparison to repulsion at 180-degree. So whenever we have to compare the stability of the molecule, so to compare stability of different structure, to compare stability of different structures, repulsion only at minimum angle should be considered. To compare stability of different structures, repulsion only at minimum angle should be considered. For example, in the structure of SF4, in the structure of SF4, this may be, let's say, suppose one of the geometry may be fluorine going inside the surface of board, this fluorine coming outward towards your side. This may be another fluorine can be present in plane of, let's say, this surface plane of board. So I hope you understand the representation of this type of bonding. So solid wedge means this bond is coming towards your side. Dotted line means this bond is going inside the surface of board, and the normal SF solid line is bond is in the same plane as the plane of the surface. More important thing is it consists one lone pair of electron may be represented as this, and it consists another fluorine here. So this may be one of the possible structure of, let's say, SF4. Similarly, in another possible structure of SF4 is with similar orientation, this fluorine going inside the surface of board, this fluorine coming outward, and this can be, let's say, in the same plane as we have, let's say, plane of the board here, and this may be the possible structure here. In this case, this is another fluorine and let's say fluorine atom here. So we have two different structure of SF4, and the possible bond angles here is, so if you see possible angles, here if you see possible angle is 90 degree, possible angle is 120 degree, and let's say 180 degree. To compare their stability, we have to just compare, or we should compare the repulsion only at 90 degree, as repulsion at 180 degree are non-significant in comparison to 90 degree, and 180 degree is obviously non-significant. So we have to just compare the repulsion only at 90 degree. So obviously this lone pair of electron is found to be at 90 degree from this bond pair of electron, this bond pair of electron, as well as this bond pair of electron. So here you can just try to imagine at 90 degree lone pair bond pair repulsions are 3, and similarly bond pair repulsion are also 3. So we have 3 lone pair bond pair repulsion, and we have 3 bond pair repulsion. So bond pair repulsion may be represented as this. Similarly, in the case of second molecule, at 90 degree here, you can simply imagine this fluorine, and fluorine here. So overall lone pair bond pair repulsions are 2, and bond pair repulsions are 4. So overall they have same repulsion. Total number, it is 6 total here, and same as 6 total here. But we know lone pair bond pair repulsion is more than that of bond pair repulsion. So out of these two structure, second structure consists less repulsion, less bond pair, and first one structure, it has more lone pair bond pair repulsion. And we have seen in the third postulate of VSEPR theory, lone pair bond pair repulsion is more than that of bond pair repulsion. So first structure consists more repulsion, it is found to be have more potential energy, less stable. So second structure is found to be, let's say, more stable. And according to VSEPR theory, the geometry of SF4 should have second structure instead of first one. I hope the concept is clear. Now, one by one, you can see different possibilities of structures here, according to VSEPR theory. So here you can just try to summarize something. So according to VSEPR theory, let's say first thing is, if you know two bond pair of electron are there. For example, this may be as, let's say, BeCl2, and for minimum repulsion between both bond pair of electron, for minimum repulsion between both bond pair of electron, you know, this bond angle must be 180 degree. You know, this bond angle must be 180 degree between both beryllium chlorine and beryllium chlorine bond. Similarly, as per this geometry is concerned, this geometry is known as linear geometry. Second one, if let's say we can have, here we can have two possibilities. Second A may be, let's say if we have three bond pair of electron, for example, it is, let's say, BF3. In the case of three bond pair of electron, which is BF3, here possible geometry may be for minimum repulsion, every angle should be equal to, let's say, 120 degree each. So between bond pair of electron, here precise angle is found to be, you know, 120 degree. Now, as per this geometry is concerned, here you can say geometry of the molecule should be this trigonal planar geometry. This geometry should be, let's say, trigonal planar geometry. Same, it's, let's say, B part. It is two bond pair and let's say one lone pair of electron. For example, this may be, let's say, SnCl2, let's say tin chloride. And in the structure of SnCl2, it is, you know, lone pair of electron. This may be Cl and Cl. So again, total arrangement of lone pair and bond pair should be trigonal planar. But now this angle should be confirmably less than that of 120 degree, as we have more lone pair bond pair repulsion in comparison to bond pair repulsion. And the shape of this molecule is either, you can say, bent, or the shape is also known as angular. So in the case of SnCl2, the shape is found to be bent or angular. So BeCl2 is found to have linear geometry. BF3 is found to have trigonal planar geometry. SnCl2 is found to be bent or angular. Same, in the same continuation, let's say fourth, and its A part is, suppose if we have four bond pair of electron, bond pair of electron is it, let's say, you can say CH4 as a geometry, a CH4 molecule in which carbon is forming four bonds with surrounding hydrogens. In this case, it is bond with hydrogen, another bond with hydrogen. This bond may further coming outward, let's say this may be H here, and this bond may be going inside the surface of board, let's say it is hydrogen here. So in the structure of, let's say, CH4, this geometry is known as, you know, tetrahedral geometry. This geometry is known as tetrahedral, and its every bond angle is found to be equivalent, and every bond angle is found to be precisely, you know, 109 degree 28 minute. So you can see it is approximately 109.5 degree. same, it's B part. We have 3 sigma bond and 1 lone pair of electron. In this case, it is found to be, let's say, suppose example. This example may be, let's say, suppose NH3 ammonia. And in the case of ammonia, this geometry is nitrogen consists one lone pair of electron. It is hydrogen here, same as, let's say, hydrogen here, and this hydrogen going inside the surface of board. This hydrogen going inside the surface of board. So as per the structure is concerned, this structure is trigonal pyramidal. The structure is going to be trigonal pyramidal structure, and if you see, this angle is found to be 107 degree. I'm repeating again. If we have 4 bond pair of electron, for example, it is CH4, this geometry is known as tetrahedral geometry. If we have 3 bond pair, 1 lone pair, the geometry is known as trigonal pyramidal geometry. Same. If we have 2 bond pair and 2 lone pair of electron, for example, H2O, and in this case, geometry is found to be, let's say, hydrogen and hydrogen here. It has lone pair of electron and it has lone pair of electron. This bond angle is found to be approximately 104.5 degree, and obviously this shape is known as bent or angular. So obviously in the shape of molecule, we do not consider lone pair of electron. So it is just a bond pair of electron which can decide the shape of the molecule. And the size of atom is much more in comparison to, size of electrons. I hope you have noted down this much. Fifth one. Fifth A part is, if we have 5 bond pair of electron, for example, it is PCl5. If we have 5 bond pair of electron and this geometry maybe, let's say, example, maybe let's say PCl5. In PCl5, it is phosphorus, this chlorine going inside the surface of board, this chlorine may coming outward, and this chlorine is found to be the same plane. It is chlorine here and let's say chlorine here. The same shape, same type of geometry as it is PCl5. In the case of PCl5, here as per bond angle is concerned, here we have three different type of bond angle. This bond angle should be equal to, let's say, 180 degree with respect to this plane. So bond angle may be 90 degree. Here bond angle between, let's say, obviously these 2 type of chlorine is found to be 120 degree, and the angle between, let's say, this chlorine and this chlorine is found to be 180 degree. This is found to be most conceptual geometry of BS-EPR theory, and it is also known as trigonal bipyramidal geometry. This geometry is also known as trigonal bipyramidal. Now in this trigonal bipyramidal geometry, here we have two different type of bonds here. One is, let's say, 3-chlorine, which lies in the same plane. They are known as equatorial chlorine. And the 2-chlorine, which is perpendicular to this, equatorial plane, is known as axial chlorine. So, for example, if you see this chlorine atom, it is known as equatorial. Equatorial, and obviously, ये जो chlorine है, this chlorine is known as axial chlorine. So we have 3 equatorial and 2 axial position. We have 3 equatorial and we have 2 axial position. So total we have 5 bond pair of electron in the PCl5, 90 degree, 120 degree, 180 degree, and the geometry is known as trigonal bipyramidal geometry. So here we have 3 equatorial bonds and let's say 2 axial bonds. The point, the things you can remember is, as per bond length is concerned, you can say PCl axial bond is found to be longer than PCl equatorial. Second point you can remember is, more electronegative element, more electronegative surrounding element, you can say. More electronegative surrounding element should be utilized at axial position for minimum repulsion. And lone pair of electron should always placed, lone pair of electron should always placed at equatorial position in trigonal bipyramidal geometry. So one by one we'll see their application of these 3 points. So you should remember these 3 points. One is, in trigonal bipyramidal geometry, axial bonds is found to be longer than equatorial bonds. Second point is, more electronegative surrounding elements should be utilized at axial position for minimum repulsion. And the lone pair of electrons should always placed at equatorial position. Such that if you see geometry of, for example, in PCl4F, in PCl4 and F2, and let's say if it is PCl2 and F4, if you see their respective geometries, in this case it is one of the chlorine atom here going inside the surface of board. This may be another chlorine atom here and another chlorine atom here. Fluorine should go to axial position and this may be another chlorine. In the case of PCl4F2, it is, this chlorine going inside the surface, this chlorine coming outward, and same chlorine here. Both fluorine should be perpendicular to this equatorial plane, and here this should be the structure. Same in the case of PCl2F4, it should be, let's say this may be chlorine atom here, this is another chlorine atom and another chlorine atom. So it is 4 fluorine basically. So fluorine should first utilize at axial position, and then we have to put fluorine at equatorial positions also. But firstly you have to occupied all axial position with more electronegative fluorine, and the remaining fluorine can occupy equatorial position. Same if we have, let's say, 4 bond pair and 1 lone pair. If we have 3 bond pair and 2 lone pair, and if we have 2 bond pair and 3 lone pair of electron. So one by one, if you take the example here, this may be suppose SF4, this may be suppose ClF3, and this may be suppose XeF2. So here we have only 1 lone pair, here we have 2 lone pair, and here in this case we have 3 lone pair of electron. Now everywhere we have to just draw, we have to just try to draw their structure. Just remember, in these geometries, lone pair of electron should always occupy equatorial position. So if you see the geometry of SF4, here this is the geometry. This may be, let's say, sulfur as a central atom. This is the lone pair of electron. This may be the fluorine going inside the surface of board, and this fluorine coming outward. So it is nothing but, let's say, that particular equatorial plane. Another fluorine is perpendicular to this equatorial plane, and this may be another fluorine atom here. So this geometry is known as seesaw geometry, seesaw shape. The similar geometry as we have seen that particular seesaw in our park. ClF3, again both lone pair of electron should occupy equatorial position, and we have one more fluorine here. This may be another fluorine and another fluorine atom, and overall this geometry is found to be trigonal planar. So in the geometry of, let's say, ClF3, this shape is nothing but, let's say, T shape. In the case of XeF2, it is xenon, lone pair of electron, another lone pair of electron, and another lone pair of electron. It is fluorine and fluorine here, and this shape is known as, let's say, linear. So in trigonal bipyramidal geometry, lone pair of electrons should always occupy equatorial position. More electronegative fluorine you should utilize at axial position. So they are the respective geometries of these molecules. I hope you have noted down this. Next one. let's say fifth one, fifth A part. If we have 6 bond pair of electron, for example, it is SF6. In the case of SF6, this geometry may be, let's say, fluorine going inside the surface of board. Here you can imagine this fluorine coming outward, this fluorine coming outward, and this fluorine going inside the surface of board. So the structure is going to be planar. One more fluorine is perpendicular to the surface of this plane, and this may be another fluorine going inward. Yeah, it is downward. So it is another fluorine going downward here. So as per this geometry is concerned, this geometry is known as octahedral geometry. This geometry is known as octahedral geometry. And just remember, it is the symmetrical geometry. So it is symmetric. As per this geometry is concerned, it is, symmetric. There is no equatorial position, no separate axial position here. And as per their bond angles are concerned, bond angle can be 90 degree here, bond angle can be 180 degree here. So there is no equatorial, no axial position. The shape is found to be symmetric. Next one, it's B part. Suppose if we have 5 bond pair of electron and 1 lone pair, and same if C part is if we have 4 bond pair of electron and 2 lone pair. In the case of, let's say, 5 bond pair, 1 lone pair of electron, for example, it may be, let's say, IF5, and in this case, for example, it may be XCF4. So in IF5, it is iodine, it is fluorine, another fluorine atom here, it is fluorine and another fluorine and fluorine atom here, and should have lone pair of electron here. So in the case of, let's say, IF5, in the case of, let's say, IF5, we have 5 bond pair of electron and 1 lone pair of electron, and this geometry is going to be, pyramidal shape. And in the case of XEF4, in the case of XCF4, it is xenon, this fluorine going inside the surface of board, this fluorine coming outward, this may be another fluorine here, and let's say this may be another fluorine atom here. Now, as per the shape of this molecule is concerned, it is going to be, square planar with 2 lone pair of electron. So this may be one of the lone pair of electron here, and let's say this may be another lone pair of electron here. And this geometry is known as, let's say, square planar. Okay, just note down this. So till now we have seen the geometries of different compound depending on the bond pair and lone pair of electron present here. So if we have to summarize all these geometries, you can see first one, or you just know, two bond pair, it is linear geometry. A two bond pair, one lone pair, it is going to be band shape. Similarly, three bond pair, it is trigonal planar. Four bond pair, it is tetrahedral. Three bond pair, one lone pair, it is pyramidal, trigonal pyramidal. Two bond pair, two lone pair, it is going to be band shape. Same, if we have five bond pair, it is trigonal bipyramidal. If we have four bond pair, one lone pair, it is seesaw. If we have, three bond pair, two lone pair, it is, T shape. Two bond pair, three lone pair is going to be linear. Six bond pair is going to be octahedral. And if we have, five bond pair, one lone pair, it is pyramidal. If we have four bond pair, two lone pair, it is going to be seesaw shape. Now, another important term is, hybridization. Hybridization is one of the important concept of chemistry. So as per hybrid state, yeah, hybridization is concerned, you can say it is intermixing of atomic orbitals. It is intermixing of atomic orbitals having nearly same energy. It is intermixing of atomic orbitals having nearly same energy to form same numbers, to form same number of identical orbitals known as hybrid orbitals. So it is intermixing of atomic orbitals having nearly same energy to form same number of identical orbitals known as hybrid orbitals. Hybridization is, hypothetical concept to explain, geometry and properties of given compound. First, we'll see more points related to this, and then we'll try to understand also. Hybridization is hypothetical concept to explain geometry and properties of given molecule. Let's say here, if we just try to see examples of hybridization, one more point you can note down. hybrid orbitals can align themselves. Hybrid orbitals can align themselves around central atom, according to VSEPR theory for minimum repulsion. So hybrid orbital can align themselves around central atom according to VSEPR theory for minimum repulsion. Now one by one, we'll see different hybrid orbital and hybridization examples. So further, if you see examples of hybridization. Examples of hybridization, in which first is Sp hybridization. The meaning of Sp hybridization is one S, any of the S, you can say 1s plus 1p orbital get intermix, and they can form two Sp hybrid orbital. So here, if you see the representation of these hybrid orbitals, as per 1s is concerned, it is assumed to be, spherical orbitals. As per 1p is concerned, it may be represented by this dumbbell shape. And as per, Sp hybrid orbitals are concerned, this may be one of the Sp hybrid orbital. It can show properties of S also. It can show properties of P also. And this may be one of the another Sp hybrid orbital. So we have two Sp hybrid orbitals. And according to VSEPR theory, for their minimum repulsion, their arrangement has to be linear. This bond angle should be equal to 180 degree, and let's say it is linear arrangement. In the case of Sp hybridization, we have 1s mixed with 1p, and they can form two Sp hybrid orbitals. The geometry is going to be linear. Same if we have Sp2 hybridization. The meaning of, let's say, Sp2 hybridization is here 1s can intermix with, let's say, 2p, and they can give, 3 Sp2 hybrid orbitals. 3 Sp2 means here you can imagine, let's say we have 1s. You can imagine this may be another p orbital, and let's say another p orbital can intermix. Due to intermixing of these orbitals, we can get 3 Sp2 hybrid orbital. And according to, Valence bond theory, according to VSEPR theory, the angle between all these three sp2 hybrid orbital should be 120 degree each for minimum repulsion. So this may be, let's say, one of the hybrid orbital here. Same, this may be another hybrid orbital here. And this may be, let's say, another, hybrid orbital here. So we have three hybrid orbital, and obviously the angle between every hybrid orbital should be equal to, let's say, 120 degree each. And this arrangement is going to be, trigonal planar arrangement. This arrangement is going to be, trigonal planar arrangement. Same, I can just draw one more energy diagram related to sp3 hybridization. So third, let's say it is sp3. In the case of sp3 hybridization, this may be, let's say, one of the s orbital. Same, this may be, let's say, another p orbital here. This may be, let's say, it may be px. Suppose here it may be, py. And this may be, suppose, pz. So it may be, px orbital, it may be py orbital. So there's the intermixing of, 1s and 3p orbitals. So due to intermixing here, we can have same number, means 1 plus 3, 4 sp3 hybrid orbital. Now this 4 sp3 hybrid orbital can align themselves in 3D such that we should have minimum repulsion. Now for minimum repulsion, this orbital must have, this type of orientation similar to, geometry of CH4. So as one of the hybrid orbital may be, let's say, look like this. Another hybrid orbital may be like this. Another hybrid orbital may be like this. And, another hybrid orbital may be represented as this. So we have 4, sp3 hybrid orbital, and this geometry is, tetrahedral. This geometry is going to be tetrahedral geometry. So you can say any hybrid orbital or यहाँ this bond angle or every bond angle should be equal to, let's say, 109 degree 28 minutes. So any hybrid orbital can either form, sigma bond, or it can accommodate, one lone pair of electron. Any hybrid orbital can form sigma bond or it can accommodate one lone pair of electron. So number of hybrid orbitals should be nothing but number of sigma bond plus number of lone pair of electron. And usually pi bond is not formed by hybrid orbital. Usually pi bond is not formed by hybrid orbital. So to find out hybridization, technically we can just find out number of sigma bond, pi bond, and lone pair of electron. For example, let's say for sp hybridization, for sp hybridization, we need, let's say, either total we have 2 hybrid orbitals here. In 2 hybrid orbitals, either we can have, A option as 2 sigma bond or B option as 1 sigma bond and 1 lone pair of electron. For example, in the case of, acetylene molecule, or you can say in the case of hydrogen cyanide, this carbon just forming 2 sigma bond and 2 pi bond. Pi bond is not formed by hybrid orbital, so there is no correlation between number of hybrid orbital required and pi bond. This carbon is also forming 2 sigma bond. This carbon is forming 2 sigma bond, and this nitrogen, it is forming 1 sigma bond, and it consists of 1 lone pair of electron also. Since out of 5 electron on nitrogen valence shell, 1 forming sigma bond, 2 forming pi bond, and another 2 electron remaining, and thus 1 lone pair of electron. So its hybrid state is sp. Its hybrid state is sp. It is also sp, and it is also sp hybrid state. So whenever we have 2 bond pair of electron, this geometry is going to be linear around it. Obviously, this geometry is found to be linear, and this geometry is found to be linear about this carbon. Another hybridization is, sp2. sp2 hybridization. In sp2 hybridization, there are 3 hybrid orbitals. We require 3 hybrid orbitals here. In sp2 hybridization, we require technically 3 hybrid orbitals here. In 3 hybrid orbitals, again, we can have either, let's say, 3 sigma bond. We can have, 2 sigma bond, 1 lone pair, or we can have 1 sigma bond and 2 lone pair. So in all cases, we should have, sp2 hybridization. For example, suppose if it is H, this may be, carbon forming double bond O here. And, it is, let's say, CH CH and it is double bond and NH. I hope this combination is better, or you can just try to say in this case, let's say it is H here and double bond N and H here, we have one lone pair. This oxygen consists 3 lone pair of electron. Deliberately, I draw the structure such that every carbon, nitrogen, and oxygen is found to have same hybrid state. In this case, carbon is forming 3 sigma bond, same as this carbon. Both carbon forming 3 sigma bond. This oxygen, it is 1 sigma bond and 2 lone pair of electron. And this nitrogen, it is 2 sigma bond and 1 lone pair of electron. So we have 3 sigma bond, 1 sigma bond, 2 lone pair. It has 2 sigma bond, 1 lone pair of electron. Such that every carbon, oxygen, and nitrogen is found to be Sp2 hybridized here. As per their geometry is concerned, this geometry should be, bent. And once we have 3 sigma bond, this geometry is found to be trigonal planar geometry. It is found to be, trigonal planar geometry. In trigonal planar, we can have 3 sigma bond technically. In next one, let's say if we have, Sp3 hybridization. So it is Sp3 hybridization. In Sp3 hybridization, here we have 4 different things. Either it is forming, let's say, 4 sigma bond. It may be 3 sigma bond and 1 lone pair of electron. It is 2 sigma bond and 2 lone pair of electron. And here we have 1 sigma bond and 3 lone pair of electron. For example, suppose if we have central atom as carbon forming bond with hydrogen here, it is chlorine, it is NH2 and let's say it is OH. Here every oxygen consists 2 lone pair of electron, 1 lone pair of electron and 3 lone pair of electron here. In the case of, let's say, this carbon forming 4 sigma bond. Here it consists 2 sigma bond, 2 lone pair of electron. It is 3 sigma bond, 1 lone pair of electron. It is 1 sigma bond, 3 lone pair of electron. So as per hybrid state of every carbon, oxygen, nitrogen, and chlorine is concerned, it is found to be Sp3 hybridized. As per their geometry is concerned, 4 sigma bond means it should be tetrahedral geometry. 2 sigma bond and 2 lone pair is bent. This geometry is, trigonal pyramidal. And in the case of chlorine, it is 1 sigma bond and 3 lone pair of electron. So 4 sigma bond, it is tetrahedral, 2 sigma bond, 2 lone pair, it is bent. 1 lone pair, 3 sigma bond, it is trigonal pyramidal geometry. and in the case of chlorine, which is forming 1 sigma bond and 3 lone pair of electron. So overall funda is, let's say, you should able to find out hybridization state of different central atom, and you should able to predict their geometry. For example, let's say first question based on this is find out, hybridization state of, every carbon atom in following compounds. You have to find out, hybridization state, find out hybrid state of every carbon atom in following compound. Let's say first one, if it is CH3, it is CH, and let's say it is double bond CH2. Yahan similarly, if it is CH2 double bond C and double bond CH2, and similarly, if it is CH3 CH double bond CH, it is CH2 and C triple bond CH. In this case, this carbon is found to be, Sp3 hybridized, as this carbon is forming 4 sigma bond. Next wala carbon is forming just 3 sigma bond, so it should be Sp2 hybridized, and this carbon is also forming 3 sigma bond, so it is Sp2 hybridized. I am repeating again, if it is 4 sigma bond, it is going to be Sp3. If we have 3 sigma bond, it is Sp2. If we have 2 sigma bond, it is Sp. This excluding the lone pair of electron, otherwise you can count the lone pair of electron also. But as per all these compounds are concerned, there is no lone pair of electron in any of the carbon atom. This carbon is forming 3 sigma bonds, so it is Sp2. It is Sp and it is Sp2. This carbon is Sp3, this carbon is Sp2, this carbon is Sp2, this carbon is Sp3, this carbon is Sp and Sp. They are different hybridization state of different carbons. Getting? So you have to just count the number of sigma bonds, particularly same. Suppose if we have another example here, this is CH3 and COOH. So as per first carbon atom is concerned, it is going to be conformly Sp3 hybrid state, as it is forming 4 sigma bond, and the next carbon is 3 sigma bond, so it is Sp2 hybrid state. Similarly, if it is CH2 and CH and CH, and C triple bond CH. Okay, just try to do this. Hybridized state. So here I'm repeating, the hybrid state of this carbon should be sp2. This carbon is, sp2. This carbon is sp, and this carbon should be sp. Depending on the number of sigma bond and pi bond. Okay, we'll continue with the same concept in the next lecture also. So in the next lecture also we'll continue with hybrid state in more complex molecules. So I'm repeating again, as per hybrid state is concerned, it is helpful to predict the geometries of the molecule and many more properties in organic and inorganic chemistry. It is one of the most conceptual part of chemistry, hybrid state. So everywhere either we have structures of organic compound and inorganic compounds. We need to know their hybrid state. So we'll continue with hybrid state in the next lecture also. So this is all for today's lecture. Thank you.